So, and you will not be able to describe that. So, it's final test.
Okay, so we've been discussing trying to understand the physics of the so-called mech geometry. And let me write the metric down again. It's S squared equals 2j gamma squared minus r squared t squared plus the r squared over r squared plus the theta squared plus lambda squared d5 plus r dt squared, where gamma and lambda depend only on theta. So this is a solution of Einstein's equation with no cosmological constant, and it represents the scaling region very near the horizon of an extreme curve like Como. If I wrote lambda squared last time, that would be wrong. This is just lambda. So there has to be a double zero that equals for this to be zero. Okay, and this has an SL2R times U1 symmetry, and the SL2R.
What the muscle maybe some of the statements is that breeds correspond to muscle.
Sorry?
What is the muscle?
J is equal to m squared, so this is extreme curve. Now, what we did, we're looking at how to reproduce the entropy formula S equals 2 pi j, and we found that in order to reproduce this, before you start doing anything, you know that you want a Virasoro algebra whose zero mode is going to be J itself. And that's the shifts of phi. So that's the U1. And we found such a thing. We wrote down, we found some boundary conditions that, among other things, demanded that m squared equals J, but not that J be fixed. We found some boundary conditions. We computed C, we computed T, and we put them together in the Carty formula, and it gave us the 2 pi. It gave us the 2 pi J. So that's a feeling. Gives us a feeling that we're on the right track. So what I want to do today is first briefly discuss the other boundary conditions that were found really by three groups: Compare, Determine, and somebody, maybe just those two. Did a problem very similar to this in a work ADS, and then somebody, then a Korean group, and also Castro and Larson. I thought that paper was the easiest to read. Computed found an alternate set of boundary conditions in which you fix the charging. No, I'm sorry, you don't fix the charging you want, but you don't demand m squared equals j, and you now your Virasoro is not of the form. It doesn't have a term in it like epsilon phi d phi. That's in what we call what do we call that? We call that the left Virasoro. Instead, there's a term like epsilon of t dt minus r dr epsilon prime of t. I don't remember the exact coefficients. And that's the Kurosawa right. And the computation of the central charge, RDR, yeah. The computation of, so this is a different kind of Kurosawa algebra because it's acting on, we can think of this all acting in an ADS2 subgroup. And so if I just draw a Penrose diagram of the ADS2 here, we'll kind of reduce all this to the ADS2 factor. What you find is, something that has reparameterizations on here. And includes a Kurosawa which has reparameterizations on here and includes the SL2R as a subgroup. So this is a long story which I'm just going to go through rather briefly. That Kurosawa is equivalent, if you think of this as two-dimensional gravity, which of course you have two-dimensional gravity. In conformal gauge, there's a conformal, residual conformal subgroup of the two-dimensional diffeomorphism group. That's the same as this conformal group here. So this conformal group here extends into the bulk in the natural way that we're used to. Not in ADS-CFD, the way that we're used to in ordinary two-dimensional gravity, two-dimensional field theory. So it's really the usual conformal group. But it's diffeomorphisms, so you might think that the central charge would be 0. It turns out not quite to be 0 because you've got effectively an electric field associated with this U1 at the boundary. And you need to, in order to preserve the boundary conditions, you need to improve the stress tensor with the gradient of the current associated with that electric field. And that gives you then a central charge which you can calculate. And so that's what Castro and Larson did.
And sorry, I'm just on. So the ES2 has two boundaries, right?
Yeah. And
here you're drawing, this is on one of the boundaries that you generate conformal transformations there? Or am I misunderstanding?
Well, it's the conformal transformations of the strip, the boundary conditions here. And because of the boundary conditions that you oppose here, there's only one conformal group. It's like the open strip. Okay. And so, all right, so that's a relatively long story, but you go through it. It's a completely different calculation than the one that we did here. And you also find C left equals 12J. C right. Sorry. You find C right equals 12J. And if you look at the entropy for, if we now have, we can now do the following calculation. So we know that these excitations carry energy, so they'll change. The L naught of this is, in fact, the L naught of this is exactly m squared minus j. You might ask whether this ddt, you might think that this ddt is energy, but it's not quite, because we shifted phi. And so it's really measuring exactly the deviation from externality.
So do the symmetries of the right moving Kurosawa change the value of j?
The symmetries of the right moving Kurosawa change the value of j. Did they commute with... Okay, so you also get, and here's the interesting point. You get another thing here, as I said, you get a U1 current algebra. So this guy here becomes part of a U1 current algebra. And so the SL2R on U1 becomes Kurosawa times U1 current algebra. And there's no generators in there that carry U1 charge. So none of those operators change J. Now, yes, sir.
Could you say something about how exactly, how the boundary conditions differ from the ones you wrote yesterday?
Let me just say one more thing about this, and then I'll answer your question. So you can look at the entropy to linear order away from externality. So again, we're kind of repeating all the things that we did in string theory 10 years ago, but now without using string theory. First we got the extreme case, then started moving out. And you find that to linear order, this matches numerically with this value of the central charge plus the Carty formula. It matches numerically the deviation of the entropy from externality. So the match is not only for the 0-point energy. It's basically, I guess, that the entropy is basically 2 pi square root of 12j over 6, which is 2j, times epsilon, where epsilon is the deviation from externality. So that, and it's normal. You have to be careful about the normalization, and careful about the normalization to get exactly the right thing. Okay, sorry, what was your question, Rajesh?
In what significant way do the boundary conditions differ from what you imposed yesterday?
Well, they're just different. They're both stronger and weaker. Some components the fall off is stronger. I actually never wrote them down yesterday. You can find them in all the papers, but they're both stronger and weaker.
Weaker in that they allow you to go away from externality, but they are stronger
in that they fix J. Now,
can I just ask sorry, my question? If you look at physical excitations in the curve geometry about externality, do they, for small deviations, do they look like excitations in ADS2, or is it that the moment you excite it a little bit, you just get rid of the ADS2?
Okay, so that comes to the reason why we can only go with a linear order. If you take the back reaction of these things, so you add a little bit of energy, and if you take the back reaction, you get so you add a little bit of energy here, that's fine, but now you let it back react, and that back reaction actually grows as you go towards the boundary and destroys the asymptotic boundary condition. Now, there's some story. This should not completely prevent us. Well, it has prevented us, but should not prevent us from understanding this situation. Because, this thing is growing slowly, and, for a very long time, it still looks very much like ADS2. And so if you put it in for a cutoff and then take your coupling constant to 0, you still have ADS2 at the cutoff. But still, nobody has ever understood nobody's understood how to deal with this, or even what exactly the right question is that we want to ask. So that's why we're stuck at linear order. And in a moment, I'm going to talk about the scattering amplitudes, and we're going to find a very compelling match between the scattering amplitudes and the predictions of the conformal field theory. But again, we're going to consider the problem like it's the problem of scattering on a fixed curve black hole that involves higher point functions in the conformal field theory, but no back reaction. Okay. Now, one very funny thing that is clearly very significant in this whole story, but we haven't really understood the significance or what we're supposed to do about it, is that the thing that played the role in sort of the right-moving boundary conditions, the thing that played the role of the zero mode of the U1 current algebra is the same. It's the same geometric isometry as the thing that as the L0 of the left-moving Versor. And so it's easy to see that if you were forget about boundary conditions, if you would just try to write down those, add to these generators the ones I wrote down yesterday, that they would not, you would get some algebra which is much bigger than a Versor algebra, some infinite dimensional algebra. I don't know what it is. So it's clear that there's no boundary condition that gives you a right Versor, a left Versor, and a U1 current algebra. There's just no room for that. And I don't really understand how this is happening. Another thing that's just suddenly sprung. So there are a number of differences with this story we're used to, but this is one of them. Another one is that, this curved black hole is it represents this field theory at temperature T equals 1 over 2 pi. That's what sort of the rules of holography as we understand them would tell us to associate. You might hope, that this was kind of Ashok's question yesterday, you might hope to find some other geometry with a different temperature. We don't know what those geometries are. And in fact, you might hope to find the vacuum. In the ADS cases, we know that the global ADS is the vacuum, and then we have all kinds of black holes here. So we can't, in this case, naively you would get to the vacuum by not identifying phi. But if we don't identify phi, we have a singularity at the North Pole, theta equals 0. So formally, the vacuum is some singular geometry, and also, if you try to change the temperature in any way, from 1 over 2 pi, you get some kind of singularity there. And I don't know how we're supposed to think about that.
What is that the temperature corresponding to this new entropy that you were
what's the temperature?
Yes, there must be a different temperature now.
Yeah, there's a different temperature. And yeah, I'm going to talk about that in a moment when I talk about it, because this comes into the superradiant scattering amplitudes. Well, let me just say a word about it now. So what is the temperature in ADS2? It's not this. In this context, the temperature is sort of the length of the identification. But here, it's something a little bit different. So what is a black hole in ADS2? There is a notion of a black hole in ADS2. And you can find it, for example, by taking an appropriate scaling limit of any black hole geometry with an extreme limit. And what you want to do is you want to take a scaling limit where you keep the Hawking temperature fixed while taking R going to R plus. And what you end up with is something, so at zero temperature, you see this metric here, which I got as the near horizon limit of extreme curve, covers only this Poincare patch. If we look at just the R, so this is R, and this is T. And there are some global coordinates for the neck geometry, which I haven't written down, that cover this whole complete maximal extension of the neck geometry. But there's a scaling limit in which you cover not this Poincare patch, but a submanifold that just looks like this. And observers at constant R in this geometry see Unruh radiation or Hawking radiation. So this is the ADS2 version of a black hole. It's just a section. You see, in ADS3, black holes get more and more ephemeral as you go down to lower dimensions, right? In 4 dimensions, it's a different geometry with different local curvature. In 3 dimensions, black holes are just quotients. And the local geometry is, you can't tell from the local geometry whether it's a black hole or not. In 2 dimensions, a black hole is really just an assignment of a region of infinity. Right? So if you say that time goes from plus infinity to minus infinity, as you go over this region, and that region is too small for a light ray to go to the other side and come back, then that's a black hole. Okay. All right. Now I'm going to move on and talk about the let me say that in a little more detail because I'm going to need it for the calculation I'm about to do.
And yeah, I have a quick question. I'm sorry, I'm confused about this. Temperature reading 1.2 pi. So if I take the entropy formula and it's 2 pi j, so it's 2 pi times n squared. So if I differentiate the entropy with respect to the mass, I just get 2 pi times 4 pi times n, which then goes as square root of j. So would that be the inverse temperature? No.
No, because this temperature is conjugate. This temperature, which we're calling T left, is the thing that's conjugate to charge.
And in fact, this is the Hagedorn relationship. Yes. Entropy is proportional to. That's why your temperature is fixed, independent of G.
Okay. So let me talk about this in a little more detail because I'm going to need it.
So maybe this suggests why you can't move the temperature away from 2 pi. In string theory, you can't take the temperature higher than Hagedorn. Because S is proportional to N, E.
There are also some background.
Oh, why couldn't I make it lower?
Lower.
This happens in some backgrounds that are supposed to be dual to little string theory, which also should have Hagedorn behavior. I remember there was some puzzle about some black hole, and there was only one temperature possible for those geometries as well.
I mean, the general thing that seems to be happening here is that there's a suggestion of a conformal field theory that has one more quantum number. We're matching it to a conformal field theory, but the conformal field theory we're matching it to has one more quantum number available to it than the curved black hole does. Now, it could be, perhaps the situation would be, we don't know that there isn't some SL2R times SL. It's not known. It's a question in general relativity whether there's an SL2R times SL2R invariant geometry which might be interpretable as the ground state of this conformal field theory, but with some asymptotic so that it can't be glued onto flat space. We don't know much about solutions of GR with weird asymptotics. It could be that this constraint on the quantum numbers is just a constraint on what you need in order to glue on the flat space. That would be the nicest resolution, but I don't know if that's...
So, to ask the question just a little bit differently, in your first SL2 that you talked about yesterday, are there any solutions with the asymptotics you impose as the correct one, different from the extreme curve that are known? Just solutions of GR?
I believe that the only ones are... The answer is yes, there are, but I believe that the only ones are ones that are differ by large diffeomorphisms.
So at infinity, they don't meet the required asymptotics you impose to define charges. Is that right? Or
No, they do meet the asymptotics.
They do.
Well, wait, which asymptotics?
All right. So you define some required asymptotics to then get a definition of charge and so on. So the falloffs have to be of some required types. And my question was, of course, the extreme curve met that requirement, but are there other non-trivial solutions which do meet it?
Yeah, the large diffeomorphisms of extreme curve, allowed by whichever set of boundary conditions you're considering.
But they don't give you a different value for C versus L naught or whatever.
No. Well,
I mean,
they can change L naught. If you echo L minus 2, you'll change L naught. Okay. So what we want to do now is I'm not going to write it down again, but we want to go back to the original curve metric. And we want to allow a slightly more general scaling. And we want to take T Hawking going to 0 with R hat going to the horizon R plus. But we want to, with the scaling parameter lambda, but we want to keep what I'm calling T right, which is 2m T Hawking over lambda fixed. And so this is a very right. So the Hawking temperature is going to 0, but so is the energy of the excitations that we're considering. And if you do that, you get a formula. I think I'll just write it as a correction to this. This R gets replaced by R times R plus 2 pi T right. This one also gets replaced by R times R plus 2 T right. And this one gets replaced by R plus 2 pi T right. Now, there's some rather complicated diffeomorphisms that you can do which eliminates this T right. So globally, this is the same as the net geometry, but as I wrote here, it's a different slice of the net geometry, and it's something which has some non-zero temperature. So at the same time, what we want to do is we want to also keep n right, which we defined yesterday as 1 over lambda 2m omega minus m. We want to keep that fixed as lambda goes to 0 in the scaling limit. So now something with omega, little m is the angular momentum. So we're talking now about modes on curve. And they're characterized by frequency and angular momentum, and omega equals m. And something with n right equals 0, that's the so-called superradiant bound. And so we want to scale energies to the superradiant bound as we scale this whole temperature to 0. And if you do this, you find, okay, so now I want to talk about, so this is the context I want to discuss. So I'm taking T right and N right fixed with lambda goes to 0. And this R, I guess, is R is equal to R hat minus R plus over lambda M probably. And there's also the same relations with phi and T that I discussed before. Okay. So, so this is what we call the near net geometry. It's like an infinitesimally heated version of the net geometry. Okay, now I want to talk about the scattering amplitudes. So the scattering of fields of arbitrary spin off a curved black hole was a subject of an enormous amount of discussion in the early 70s. The problem was amazingly kind of completely solved, which looked rather impossible at first, but it turns out that you can separate the wave equation. Chandrasekhar famously separated the Dirac equation, and after Tchaikovsky had separated the scalar wave equation, and then Tchaikovsky and Press separated the wave equation for arbitrary spin. And so then you get some differential equations that you still can't quite solve. ODEs for the radial and the angular part of the wave functions. They're called Hume functions, or sometimes Tchaikovsky functions. And but there are two limits in which you can get very explicit about the solutions. And one is the low frequency limit, omega goes to 0, where the wavelength is small compared to the long compared to the size of the black hole. But the more interesting limit is when omega is equal to angular velocity times m, which is just m over 2m. That's when you're scaling near the superradiant bound. And in fact, you can check that if you're not near the low energy waves, in fact, will reflect off the black hole before they ever get into the neck region. There's a barrier that keeps them out of the neck region. And it's only the things which are scaled right to the superradiant bound which can get into the neck region. And so the energy above and below the superradiant bound is, of course, the energy with respect to this T. So it's the thing that you would. This is the thing that you would expect in this near region. So that's the scaling limit we want to take. We want to consider black holes which are near extreme and energies which are near the superradiant bound. So there's some formulas that these people derived.
Don't you have a non-zero scattering cross-section even as omega goes to 0? And absorption cross-section even as omega goes to 0?
You do.
So even as omega goes to 0, some of the stuff goes in. Right?
Some of the stuff goes in.
But more goes in. Yeah.
Well, some of the stuff goes in, and there's something very interesting about this. And actually, Moldesina and I wrote a paper about this in 96 or something. And actually, the scattering amplitudes look like those of, I'll come back to this in a moment, they look like those of a conformal field theory. But it's not this conformal field theory. And actually the suggestion there is that there's somehow, okay, again, a lot of speculation, that there's actually two conformal field theories at different scales. You have the stuff at omega equals 0 is governed by one conformal field theory, and then you go do some RNG flow to further in. So those wave functions simply don't penetrate this neck region. So we don't. They're not governed by the conformal field theory that I'm talking about.
But if they go into the horizon, don't they have to penetrate the neck region?
They don't go in.
It's different from the Schwarzschild, right? Because of the angular momentum barrier here, isn't there? I mean,
No, is there a non-zero absorption cross-section? If there is a non-zero absorption cross-section, goes through the horizon.
I mean, is there? I mean, in that case, there's an area, just an area, and so on. Here, for omega going to 0, is there?
It's one base area. Because that's why eta by S is 1/4 pi.
In the Das Matrix calculation, it was just a Schwarzschild.
But isn't this absorption cross-section somehow universal? I mean, that's why I thought eta by S is always 1/4 pi.
Maybe I don't have a good answer to your question, Charles. Okay, so I think somehow the wave function is exponentially suppressed in this region. Now, okay, wait, where was I? Okay, all right. So now there's a formula, a very interesting formula, which I'm going to write down. It's kind of complicated. So what I'm going to write down is less complicated than the most general formula in precedential Minkowski. It's certainly less complicated than the most general formula in Thomas Sager's book, some of which took hundreds of pages to write out. But it's still pretty complicated. And it's a formula for the absorption cross-section. And this is just for the scalar. We've also done matches for charged fields and spinning fields and so on, but I'm not going to try to go through that. So you have 8 pi t Hawking, where, of course, since this is a classical calculation, you just want to think of this as a surface gravity, to the 2 beta. Now, what is this beta? Well, beta is given by beta, and this is for a massless scalar, though adding a mass is not significantly complicated. It's k bar L minus 2m squared plus a quarter. So if the theta phi things were spheres, then we would have k bar L is equal to L plus 1. And this would be what beta was. But in fact, the sphere in Kerr is squashed, and the eigenvalues of the harmonics on that sphere they obey something called the Hune function. It's the Hune equation or the Tarkovsky equation, and they can be computed only numerically. And you can look up, I think Gradstein and Rishik has tables of what these are, and they're labeled by one parameter F. Okay? So when you specify an incoming wave, you have to specify what L is, you have to specify what M is, and you have to specify what its energy is.
This beta can be imaginary.
Beta can be imaginary, and that's important. And that's related to the instability. Though,
just to clarify.
but let's first consider the case of real beta and then we'll see what happens when beta gets imaginary. Yes?
So this is the integrated cross-section, but in they scale to the super-radiant. Is that what you said?
Well, when I write it out, I'll explain what the it's going to depend on n right over t right. So, yeah.
So this is for long-wave absorption. Omega goes to 0, and usually
No. Yeah, so
sorry, I didn't quite understand.
Let me write the formula out before trying to figure out what the formula means. It's good to put it on the board. Okay. So then we have a pi times gamma 2 beta squared gamma 2 beta plus 1 all squared. And then gamma of a half plus beta plus im to the 4th times gamma of a half plus beta plus I n right over 2 pi t right squared. Okay? So, well, let's see. All right, so I've said what beta is. M is the angular momentum of the mode. We're doing this calculation, we're going very near extremality, and sort of linear order away from extremality, and we're taking the energy of the quantum, the right moving energy of the quantum we're scattering to scale in the same way as the temperature. But we're having arbitrary left moving energy, which is just M. M is the left moving element. Now, one of the things about this calculation is, when we were discussing the conformal field theory from the point of view of the net geometry, we had to talk about boundary conditions, and that was the level. But when you do the scattering calculation, there's no boundary condition. You're matching. Maybe there's some implicit boundary condition, but you're just matching near and far. The calculation is telling you what boundary condition you want. So that's how this calculation is done, right? You have a near region wave equation and a far region wave equation, and the overlap region has to be large. And in order for the overlap region to be large, we need small n right. A more familiar thing is small omega. Okay? But it works the same way here. Okay, so it turns out we completely reproduce this formula, including all these factors here, and not the 2 pi's. And what's puzzling about this, which puzzled us for a long time, this looks like kind of a standard thing, those of you who are familiar with it. But we've got this funny 4th power here. And that works out in an interesting way.
You said that you don't get 2 pi's? So it's not exactly in the boundary where you don't get this number exactly.
These guys. You have to worry about the numerical normalization of your vertex operators. I'm not sure that's a calculation we've even done in string theory, where we have everything.
Are you going to say which CFT correlator that reproduces?
Yes. So, all right. So now let's suppose let's go back a second. So now I've just quoted the gravity result. So now let's suppose we have a scalar field phi, and I'm still thinking it to be massless for simplicity. And we can rewrite this, since we can separate the wave equation, we can expand this as e to the I m phi minus h right t s of theta f of rho. where rho is not quite r. Rho is the radial variable in the global coordinate system, which I haven't bothered to write down. You can think of rho as r, and you won't be too far off. This would also be true if I made this a function of r here, but I want to find the highest order states in a second. Okay, so again, n is the left-moving quantum number. It's related to d by d phi. And h right is the right-moving quantum number. It's related to d by dt. And now we can take L0 bar phi is equal to h right. Oh, okay, this is automatic in its ansatz. And Q0 phi which is d by d phi, is equal to m phi. So with this ansatz, the wave equation separates, and we find that 1 over theta, 1 over sine theta, d theta, sine theta, d theta, s is equal to, or minus m squared over sine squared theta plus m squared sine squared theta over 4 s is equal to k bar L s. So that defines the k bar L, the eigenvalues of this equation. This is not the usual Laplacian on the sphere. Now, we can write down the generators of the SL2R isometry, the differential operators on this net geometry. And we can write down, so this is, of course, comes from box phi equals 0. That implies this, given this. But then the radial piece we can write as using the usual tricks. We have that h right minus 1 minus L bar minus 1 L1 on f of rho is equal to k bar L minus 2m squared f of rho. And so now...
Do you mean L bar?
Yeah, I mean L bar. So now, so this is just the Laplacian using the commutation relation. And now we want a highest weight state. And so we find that for every field of mass m, so now we need, so we take L bar 1 f equals 0 for a highest weight state. We drop this, then we get an algebraic formula for the conformal weight of the scalar field, which is h right equals a half plus or minus beta, where this beta is the same as this beta. Okay? So these betas that are appearing all over the place in this formula are indeed the conformal weight, the right-moving conformal weight of a scalar field in the net geometry. And if I put in a mass, so I can compute this for any I could compute this for anything, higher spin field and so on, and so we have all those formulas. Okay, now we don't have a formula for h left because the net geometry has only the manifestly a U1 subgroup of that SL2R, but we're going to assume, so we're going to say, obviously, that there's an operator O phi with h right, h left of O phi is equal to a half plus beta, a half plus beta. In other words, we're going to assume that h right is equal to h left. Naturally, you would expect h right minus h left to be an integer, and though that's not so obvious in this context. But anyway, this is what we are just assuming. And in general, when we do the calculation with fields with spin, like for spin 2, we take the difference to be the spin. We did the direct fermions and so on. So when you do that works. So now we have h right and h left.
But the solution with the minus sign, does that roll?
I don't. We just took the plus sign. Of course, the minus sign would be important when beta becomes imaginary. But yeah. Oh, of course, you can also relate this to the fall off of solutions at the boundary, and the ones with the minus sign are in danger of not falling off nicely at the boundary. That's part of the logic. That sign. Okay.
So this was an assumption, taking h left. I mean, it's a reasonable yes, but it comes.
Yeah. And we're also going to assign a U1 charge. Okay, so here's what we do. So now, if you want to compute the absorption probability, so how do we think about this? We want to think about it like this. Here is the asymptotically flat region. And then there's some boundary region where you glue onto the neck region. And now what you do to compute the scattering is you replace the neck region with the dual CFT. And when some classical scalar field, let's call this some R cutoff, and it's important, of course, that the answer not depend on our cutoff, and that is what becomes conformal invariance. That's why they have to be conformal invariant, otherwise it would depend on our cutoff. So what we have here is a coupling phi at our cutoff to some dual operator O phi. So we send something in, then we act with an insertion O phi, we compute some two-point function in the dual CFT, and then we let it come back out with the same coupling. Okay, so it's the near horizon piece of the macroscopic scattering amplitude that we expect to reproduce this. Now, when you go back up and look at this formula up here, we've got this gamma of half plus I beta plus beta plus I n to the fourth. But of those four powers, two come from the near horizon calculation, and the other two are the value of phi of RC at this boundary. What? We just computed. Yeah. If you look at the amplitude of phi of RC at this boundary, it's gamma of a half plus beta plus IM squared.
So conformal field theory does not live in flat space. So maybe I misunderstood that. So the path that you've got drawn with the wiggly lines, that's already far from flat space?
Well, this is the neck geometry, it's not flat space. But the conformal field theory, no, it just lives on the T phi cylinder.
So just in flat space, okay.
Yeah.
So it's just propagation of the scalar field in flat space gives you that phi.
No. Because the boundary of the near horizon region This boundary is already out of the flat region.
Out.
The place where you do the matching
Right.
in this context is out of the near, is not flat.
So then it sounds like conformal field theory doesn't live in flat space, it's a curved space. Because
Well, the conformal field theory lives on a world sheet, right? So I don't know what you mean by that statement.
what I mean is
The
that
boundary of this region is a flat cylinder.
But, so there's a gravity calculation, and you want to compare that to, well, one way we usually did it with D3 branes is putting D3 branes in undeformed flat space and coupling the operators to something propagating in undeformed flat space. That's not what we're doing here.
It's morally the same thing, but the geometry is different. So when you do the matching, you know, the near horizon region doesn't match on to flat space in the same way. It matches onto a curved space.
Right.
I'm missing something here, sorry. Of course, the solutions to this problem are already known by Tucholsky or whoever. So now when you said that you had to assume something about HL, you know what the generator of HL is, right? In terms of d by d phi and d by dr and so on. Isn't that right?
No. Well,
You know, I thought you wrote down that algebra. Did you write down that algebra yesterday for us with all the Ln generators and so on, including the Z?
yes, but we don't know, we can't write the Laplacian. We can't write this Laplacian in terms of those generators. We have formulas for those generators, but we can't write the Laplacian in terms of those generators because the geometry is not invariant under those SL2Rs.
But HL here isn't the eigenvalue of L naught.
It is, but sorry, by this H here, I really mean the highest weight. I really mean the highest weight.
I was just maybe being simple in my head. I thought the solution to the wave equation is known, and then we want to figure out what value of HL it corresponds to. So if you know the generator of HL, you just act on it and you figure it out. Am I thinking wrong?
Maybe there's a better. Maybe we can. Maybe there is some way to do it without stating it as an assumption. But this trick doesn't work.
You know, in the old D1, D5 system, so one calculated the scattering cross section with some particularly flat boundary conditions, and realized that most of the absorption is taking place in the net region.
Yeah.
So there was an answer there. And that answer matched with the calculation, the conformity theory. We do the finite temperature Rings function and look at the imaginary part. So it's exactly matched. Now this additional power, this 4 that is there, I didn't understand this part. I mean, you're saying that the 2 and 2 come from the conformity theory, but the additional mod gamma half plus beta plus I squared somehow is related to this wave function.
You know, it's just that there's two. It's just that the geometry is different, and this is already what happens when you try to solve the space-time wave equation. You know, you have two regions. One is already you have the near neck region, by which I mean this finite temperature thing. And you glue it onto this piece, which has no T right in it. This, okay? And so, the thing that you meet, now maybe there's another way of the thing that you need is you don't need a flat region. Now, you could, if you wanted, divide it into 3 regions. Sort of an intermediate region which has no T right in it, a flat region, and then a near net region. And there might be some sense. See, this square of this thing was the thing that Moldacina. See, that's there even when omega is 0.
Yes.
This square thing looks like a conformal field theory correlator. That's what basically Moldacina and I computed, because therefore omega would be 0. But it's not coming. That square thing is coming from this region. So maybe there's also a conformal field theory at a higher energy scale in this region. And then you have some RG flow and you get down to this near neck region. And it's also interesting because, I'm obviously not going to talk about it, but there's Fermi C. The Fermi liquid is sort of living out here. So,
and then if you have these combined conformity theories, then they would really live in flat space. Then they would really live in the uniform background.
Maybe there's a story like that.
But is there any scaling? Is there some kind of a limit that where you just get that second region and get some different asymptotics?
Yeah. I think there is a region in which you can. Yeah. Basically, this would be neck. And this would be near neck. It's important that this is not exactly neck, because we need to see this piece here, the T right.
Sorry, isn't neck? I thought neck was near.
What's the difference between neck and
I thought neck was
near. Near neck is the finite temperature geometry. It has a T right in it. And in order to have something non-trivial to calculate, you have to be keeping that. You don't see anything about the right movers in the CFT if you don't, in order to make a statement, we have to be in this regime. Otherwise, everything becomes vacuous. And so we have a near neck region here, which is then somehow glued onto a neck region, which is then glued onto flat space. And maybe there's some sense in which, but I don't know. We didn't try to understand it that way. Just because there were so many other things.
From this point of view, isn't it more surprising that the near neck region has a CFT interpretation in that for the neck region you develop the story about the zero algebra and so on and so forth, like in last talk and so on. That was all at zero temperature. Zero T, right?
Yeah. Let me go on and see, you see, because to get something interesting, you have to write down a formula using finite temperature correlators. So we have to be able to put everything at finite temperature. You have to complicate the situation to get an impressive match, right? Otherwise, if you put everything at zero temperature, they'll match, but it'll seem a little backwards. So what did we do? Well, so the absorption cross-section is, so we define some green function, g of t plus t minus is equal to some O dagger sub phi of t plus t minus O of phi of, say, 0. And then we, so the picture here is we have the asymptotic region, and then we have our dual CFT here. We send something in, it couples to O phi, propagates in the CFT, couples to O dagger phi, and then goes back out. Okay? So we have a 2-point function But the two-point function that we want is, usual nonsense, is related by a formula like dt plus dt minus e to the minus I omega right t minus I omega left t minus g of t plus minus I epsilon g of t plus minus I epsilon minus complex conjugate. Okay. So now this two-point function g in a conformal field theory is determined by conformal invariance. So if the operators have weights h left, h right, and chemical potential q right, and we have a temperature T left, T right, and chemical potential omega right, then this G goes like minus to the H left plus H right. Pi T left over sinh pi T left to the 2H left, a similar factor with interchange of left and right, and then because of the potential, chemical potential, there's a phase e to the I QR omega right T minus. Okay. So now, we have to decide what we use for everything here. We have this formula now, but we need to say what we do with H left, H right, Q right, T left, T right, and omega right. So I've already said what we did with H left and A right. We take Q right equal to M, because that's because it plays the role of the U1 current algebra. We take omega right equal to n right plus m omega right. And that's because we're talking here about the eigenvalue not of the near horizon t, but of the far t. We take q right equals m. Sorry, I already said that. We take t left equals 1 over 2 pi. And we take t right, that's what we've been calling t right. And then here's the funny thing, is that we also take omega left equals m. So we take this formula for an operator where omega left, the zero mode of the left Versaro algebra, is the same as the zero mode of the U1 current algebra. And that is motivated A, by the fact that it gives us that it works perfectly, and B, by the fact that geometrically these zero modes were the same thing. We still don't understand how we're supposed to think about all this, but it's clear we could never match to this formula because we simply don't have enough quantities associated with the quanta that we're scattering to match to all this data.
So HL has nothing to do with. So HL was meant to be the eigenvalue of the left moving neuron. Are you saying it's a different neuron?
No, HL. HL is the conformal weight of the operator, of the highest weight operator, right? But now you're doing some transform of that, right? You're taking 2-point of operator, and you're doing a Fourier transform of some operator at some, and physically that's what you're doing, right? If you scatter off here, you'll send in with some L mod eigenvalue, which will have nothing to do with the actual highest weight of the fundamental operator that you're calling to.
So, and in the pre-absorption, are both omega r and omega left multiplied by t minus?
No, this function is t plus.
And in Green's functions is 1 by t minus?
So discontinuity.
And the Green's functions of a conformity theory on the line or on a circle?
On the surface. Finite temperatures.
They're on the line. If you're on a circle,
You get images.
you get images. And that's the same thing. Again, we encountered this in string theory, because you have to ask, why don't those images
Those long strings.
long strings? So, in fact, yeah. So actually, essentially, again, Maltesina and I did exactly this for the stringy black hole, and that was the first way that we understood that they really were described by a conformal field theory in every sense of the word. But of course, there we had some microscopic theory we were matching. But at the end of the day, our calculation didn't actually sort of proceeded in the same way. We just said, suppose there's a field of mass m in string theory, this would be its conformal way, and so on.
So let me get back to this question of you are doing a finite temperature calculation, so the time is compact, right?
No. This is a formula. Something wrong with that. I need a T plus here. T plus is just a coordinate on the plane. You could ask why it's the plane, not the cylinder. That's the question Shiraz just asked.
Yes, but finite temperature, so I'm confused.
Well, in Euclidean space, this can be periodically identified. But, I mean, that's just a statement that if you consider correlation functions of conformal field theory at long times, they'll die exponentially. I mean, it's periodic in Euclidean space. That's what it's supposed to be.
And just a small clarification. Omega factor R is the same as what the omega H, which is 1 over 2.
Oh, yeah. Right. So I have to say what I do with that. Right. I said I take omega right equals 1 over 2m. It's the black hole.
The central charge doesn't enter this formula.
No. So obviously, okay, now you can do this integral and so on, and for the to get from the Green's function to the absorption cross section, and you then get precisely what's on top, but with a square instead of a fourth power, and the square comes exactly from this. And in fact, if you keep track of the factors, I believe we've even got those factors of the powers of T walking and the factors of gamma of the betas to match. Okay. So now let me say, okay, so that's a very detailed agreement. And somehow what's interesting here is we didn't have to, there were no boundary conditions at all to be picked. But still the symmetries, those various symmetry generators act on these correlation, the symmetry generators for both the left and the right movers constrain the form of these correlation functions. And so they really end up being correlation functions of a non-chiral conformal field theory. And it's because of this match that we're in our first paper we were sort of agnostic about whether curves should be dual to a truly extreme curve should be dual to a purely chiral CFT or the chiral half of a non-chiral CFT. But now things seem to be matching very well for the other half of the CFT, and so it seems like that is the way to think about it.
So if you didn't put omega L equals m, this integral could still be done and so on, and what would you get?
Well, you mean you just left omega L as omega L?
Yeah. It still makes sense that integral, is it or not? Or are you
yeah, the integral makes sense. You just get some expression that involves too many parameters to be compared to any scattering amplitude off a curved black hole.
Specifically, I was saying that there's two factors. I mean, there's the power, second power and the fourth power.
When you're scattering a scalar field, the incoming wave is characterized by capital, the script L, M, and N right, you say. Yeah, that's how we want to think about it. M and N right. And so, if you have some formula involving more variables than that, you have to say what you're going to match it to. Yeah.
So, Andy, in some familiar case like V3 brains or AES5, this kind of agreement was enough to then make a more precise statement about AES CFT. Right? Namely, if you wanted to compute the correlators of the CFT with source terms, that is equivalent to doing something above computing something.
Yeah.
And that must be true here too.
Yeah.
So there is a reasonably precise statement that I don't know what it is, near neck or neck region. If you're working there with can we make the precise statement? Take this neck region, put this kind of boundary conditions, and then do a bulk calculation, and that is the same as coupling the CFT to external sources and computing.
Well, we can say whatever we want. It's more a question of what calculations we can do.
Yeah. Given this detailed agreement,
Yeah.
does that translate to? Seems like it should translate.
Yeah. Well, you could have made that already. You could have been tempted to make such a statement, or make such a conjecture. I suppose I did already yesterday, just from the analysis of the asymptotic symmetry group, and then this is evidence in favor of the conjecture. Let me just say a word about something rather important, and then I guess I'm just not going to talk about the Fermi liquid story. Beta can be imaginary, but there's no problem from the point of view of the Tucholsky-Press Chandrasekhar calculation of letting beta be imaginary. Those just correspond to, physically it's completely understood. It's related to the superradiant phenomenon. In fact, not everything which is superradiant has imaginary beta. That's something that puzzles me. But beta can be imaginary, and those always are the superradiant. Such ones always are superradiant, and they have the property that if you throw them at the black hole, they come back with a larger amplitude then they went in. That's classical super-rating. And so you can compute it. You have to be very careful. So now there's a formula like the one in the top that has been computed, with classical calculation. And it's a little more complicated. It's not just this formula with imaginary beta. There are two terms which kind of beat off each other. And it's a more complicated calculation. And that calculation, again, is reproduced by taking the analytic continuation of this formula. So now we imagine that the dual operator has an imaginary conformal way, and then conformal invariance still determines the form of its 2-point function, and so you can still write down this formula, and some things that should have been positive are now negative, or something like that, and you still at this level get a match. So I think the challenge is to kind of understand what this kind of thing means in conformal field theory. And since I'm running out of time, just one comment I want to say, just to entice you, I suppose, to read the paper on the Fermi liquids, that somehow this all has to do with Fermi liquids. And one of the things that has been realized in some of these examples is that these Fermi liquids, there's a conformal field theory governing the fluctuations of the Fermi sea, and those they're often imaginary. Some of those things can have imaginary conformal weights, and at least in some contexts, in its matter context, it's understood what it means. And there's another reason for thinking about Fermi liquids here, and that is that, again, if you think about string theory, the way you would make an extreme per black hole, say you could take the D1, D5 conformal field theory, you could start filling in the right moving fermions to a very large level, bigger than the central charge, and then that has a new near horizon limit, which is an X geometry, and perhaps the relevant low energy degrees of freedom there are the ripples on the surface of the Fermi sea. And all of this is very vague, but it seems to all be connected. And the third thing is, as we've shown in our papers, that it's simply the case that if you take the Kerr black hole and add a free fermion, and then take a classical limit, that there's a well-defined classical limit in which there in fact is a Fermi sea that extends well outside the black hole, and there are light excitations of that sea. Okay, so that's somewhere I think the subject is going, but I've talked way too much now, so I'll take questions.
That's not Hawking radiation then, right? See, this calculation that you showed.
There's no Hawking, there's, strictly speaking, Unruh-Starobinsky radiation was the fact that an extremal curve quantum mechanically radiates was discovered by Unruh and Starobinsky and was before Hawking's paper. So it's really wrong to call it Hawking radiation. Yeah. But it's not, they aren't very different. Unruh-Starobinsky radiation and Hawking radiation are really not very different.
Physically, there is not much difference between the fact that the dimension and the imaginary. It's the same process. Some stuff is falling in and it can get locked.
When the dimension's imaginary?
Yeah, that's what I'm asking.
Well, yeah, I mean, I guess the statement is that the way that the external world couples to the conformal field theory involve, I mean, there's always operators of imaginary dimension around, right? I mean, we take a free field and we're going to take, I don't know, e to the kx with k imaginary. That'll complex, that'll have imaginary dimension. You usually just don't say that they're physical states associated with such things. But here, we're perturbing the conformal field theory with some operator. The fact of throwing a graviton or scalar at it involves perturbing it with some operator that has an imaginary conformal dimension.
So the absorption is negative when
The absorption certainly can be negative when beta is imaginary.
So in the VSCFT, these absorption cross sections were kind of one way, an early way of finding evidence for the conjecture, but then you could also sort of work just within the near horizon region and do a gravitational calculation where you have boundary conditions for some scalar. You basically find that.
But that is what the absorption calculations were, right? Because you divided it into a near horizon region calculation and a far.
But yeah, so you could have done a similar thing. In principle, you could have done a similar thing here, where just working within the near horizon curve.
We could have done that, but we could have done that. We could have done that, and that would have amounted to. But I think it was important to make contact with that work from the 70s.
Sure.
In other words, it's nice to have a new way to derive old results, and nobody was ever interested in that, in that particular.
So if you were really ambitious, you could also try some kind of 3-point function here.
I mean,
is there a graph by doing some calculation in the near horizon thing, or do something analogous to these 3-point? That would be a strong check that there might be some dual conformal field theory.
Does the net geometry have like a boundary? Code mentioned, form of your.
Yeah, that's very confusing. One thing that's clear, I mean, of course it has a boundary which is three-dimensional because, it's a four-dimensional region, the boundary also. But you're probably wondering about the conformal boundary. And I think the conformal boundary is not the right concept. And this is also true. This is all, of course, very closely related to the kind of things that Rajesh has been talking about. When you have, you don't have a conformal invariance which acts on, which you don't have sort of a conformal cylinder at infinity the way that you do in India's theory. I mean, one thing you can see if you just naively take R to infinity, you see that the coefficient of dt squared grows much faster than the coefficient of d phi squared. If we were doing ADS, there would be an R squared in front of here. And so in a sense, the boundary seems, if you use the usual idea about conformal boundaries, you would conclude that the boundary is one-dimensional. But whether it's space-like or time-like will depend on whether the coefficient of dt squared is space-like or time-like. And that will depend on theta. But I think the upshot of that is that the conformal boundary is just, it's not, we're doing some kind of anisotropic scaling here. And the conformal boundary is not quite the right concept. And actually, Rojava wrote a paper which seemed to have some, looked kind of interesting, seemed to have the generalization of the notion of conformal boundary to the case where you have an anisotropic scaling going on. So,
are the super radiant modes in it for the, at least for say bosonic fields, tied to fields which lie below the DF bound from the point of view of the algebra?
Not quite. The ones with imaginary beta are the ones that will. Okay, it's a BF bound. It's a modified BF bound in the presence of an electric field. And
that's
what you meant. It's the ones with imaginary beta, which are a subset of the super radiant ones.
So in a sense, you normally we believe, at least if you take the imaginary beta ones, we believe in higher dimensions, say that if you have these fields which lay below the DF bound, you have tachyonic instability and so on. And here you're saying the end product of that tachyonic instability is to form a condensate. Is that to some sort of these tachyons? Is that the picture?
Well,
or that doesn't seem to be the case.
For bosons, I think it's just an instability. For bosons, it's just an instability. It's an instability which you can make slow. It disappears in some sort of classical way. So there might be some context in which the conformal field theory doesn't disappear so fast that we can't study it. But there is an physical instability of current. It persists persists here, and the goal should be to understand it in conformal field theory terms. And I'd also like to recommend a paper by Amparan and Diaz and somebody else called superradiance, and they looked at the problem of superradiance in the stringy black holes, and there they got there's also an instability, and they were able to understand in detail how to match this instability.
That it was some kind of Bose condensation.
Exactly. It's like a Bose condensation. Now
here it's
well, no. Here it could be what I've said. Here it could be fermions. If it's fermions, then something more interesting might happen. You might fill up the Fermi state, and that could kill the instability. But in general, there's also bosons around.
I guess what's confusing me is the physical extreme curve black hole has